Hi, this is Dr. Swapna. Welcome to your Learn Lab, your one stop for learning. I'm back with a new video, this time on the theory part of the chi-square test. So let's dive straight into it. What is chi-square test? Chi is a Greek letter denoted by this symbol. So we can also write chi-square test as chi-square and test. This was developed by Carl Pearson in 1900. So this test is also called Pearson's chi-square. A chi-square test is a non-parametric statistical test. I believe you have already watched my video on ANOVA where I have already explained what a parametric statistical test is. So I'll not be explaining this here and we'll just go forward. So a chi-square test is a non-parametric statistical test used to compare observed results with the expected results in any study or research. Let me explain what observed results and expected results are with a quick example. In general, we say that blue is for boys and pink is for girls. So I personally don't agree with this, but just for the sake of having an easy example, this is the first thing that came into my mind. So we will take this as our hypothesis that all the boys prefer blue and all the girls prefer pink. And now I decide to study the relationship between gender and their preference for blue or pink. I collect the data and I talk to a number of people and I tabulate my data. Okay, so in one column, I have the gender of the person I have interviewed and the preference of the color for if the person likes blue or pink. Now, what is my expectation? My expectation is that all the boys whom I have talked to should have opted for blue and all the girls that I have talked to should have opted for pink. But my observation table may not give me this expected result. According to my observation table, there might be a few or even a larger number of boys who have opted for pink and a similar case for girls who have opted for blue. So clearly my expected results are different from my observed result. Now I can use a chi-square test to check if the association between these two variables, that is the gender and the preference for the color, are significant or not. That is, it tells if the difference between the observed data and the expected data is due to chance or it is due to an interaction between the variables under study. I hope that is clear to you. Let us look at some of the textbook definition of chi-square. Sometimes in the examination this question comes to define the chi-square. So it's better if you write the textbook definition. So first definition we have is from Garrett, 1981. He defined chi-square as the sum of the squares of the differences between the observed and expected frequencies divided by the expected frequency in each case. This may sound a bit difficult, but this is the easiest definition you can see, because this definition actually tells you the formula of the chi-square which you will be using while computing the questions. So chi-square is the sum, which we denote with sigma, of the squares of the differences between the observed and expected frequencies, or it is the sum of the square of what? Difference between what? Observed and expected frequencies divided by the expected frequency in each case. See, this is the formula of chi-square. Chi-square is sum of observed frequency minus expected frequency whole square divided by expected frequency. This formula you will have to learn when you learn to compute the question, and this definition is where the formula comes from. So Garrett 1981 defined chi-square as the sum of the squares of the differences, sum of the squares of the differences between observed and expected frequencies divided by the expected frequency in each case. The second definition given by Guilford in 1973 pretty much says the same thing but using different words. So he defines chi-square as the sum of ratio where each ratio is a squared discrepancy. So this is what he calls a squared discrepancy of an observed and expected frequency. Okay. What he's saying is that chi-square is a ratio. And what is this ratio? It is a squared discrepancy of an observed and expected frequency. By discrepancy is simply meaning the differences. So these are the two definitions that you need to study for your exam. Now let's look at the assumptions for chi-square test. We studied that chi-square test is a non-parametric statistical test. This means it will not meet any of the assumptions of the parametric statistical test, but it can have its own assumptions. And now let's see what are its assumptions. The first assumption is that data should be quantitative or it should be in numbers. Only if it is numbers, then you can apply the formula or statistical tests. The data should be independent. The data should be independent of each other. The third one, the data should be in the form of frequencies. Now, what does this mean? What is a frequency? Frequency is the number of times something happens. Um, okay, if in case of the example that we used earlier, the number of boys opting for blue is a frequency. Number of boys opting for pink is another frequency. Similarly, number of girls opting for pink is a frequency. So I hope you got what frequency is. So our data should be in frequencies for us to be able to do a chi-square test on it. It should not be in percentage or ratio form. If the data is not already in frequencies, it should be convertible into one. Like any form you get the data in, it should be in a form where you can easily convert that into frequency. Only then you will be able to use chi-square test. The fourth assumption is that the data should be discrete and not continuous. This means the data that you get should have a value, like a concrete value. It could be 2 or it could be 4, whatever it is, it has to be a single number and not continuous as in ranges. You cannot say that the number of boys who opted for blue is between 4 and 9. This is a range, this is a continuous data. And if at all you have it in a continuous form, it should be convertible into discrete form. Okay, moving ahead with the assumptions. The sample should have been randomly selected. What does this mean? Each unit or each person in the population should have equal probability to be chosen into your sample. Or if you're studying about the color preference and the gender, every male person should have equal probability of being chosen into your sample. Similarly, every female or the girl should have equal probability of being chosen into your sample. This is what is called random selection. If you are choosing a specific set of people just because you know what kind of color they would have preference for, then this is not random, because the rest of the people do not have an equal chance of participating in your study. So this would give you skewed results, or a result, kind of result that you know will be giving you an expected result that you actually want, which is not a good practice also. So the assumption here is the sample you are using should have been randomly selected from the population, where each individual has an equal chance or probability of getting selected for the study. The next assumption says the sample size should not be too small. If it is, then it may give inaccurate results. Larger the sample size, the less it would be affected by chance. This is one of the very important assumptions, that the sample size should not be too small. The next assumption says if there are only 2 observations, the expected frequencies in each cell should be 5 or more. This means if your data table has only 2 frequencies, okay, then the expected frequencies in this case should not be less than 5. It should be either 5 or more than that. In case if your data table has more than 2 observations, then not more than 20% of the expected values should be lesser than 5, and no expected value should be lesser than 1. Now, this is also a very important assumption, that if you have more than 2 observations in the data table, then not more than 20% of the expected values should be lesser than 5, and no expected value should be lesser than 1. If the above two conditions are not met, then chi-square should not be applied. If you apply the chi-square in such cases, what happens is that the result you get will be statistically insignificant, in which case you will have to accept the null hypothesis. Accepting null hypothesis means there is no point of you continuing with the study. So in any case, what we aim for is to reject the null hypothesis so that we can actually continue with our study. So these are the assumptions of chi-square test. Let's see what is chi-square distribution now. Chi-square distribution is the sampling distribution of chi-square. What is sampling distribution? Sampling distribution is the probability distribution of a statistic. This means it's a distribution, or you may say it is a graph or any representation that shows the different values your statistic can take. In this case, chi-square. Okay, it shows the different values your chi-square can take if you test more than one random sample from the population. Again, let me correlate this with you, the example that we were using. You chose a group of, say, 25 boys to record their color preferences, and then you do a chi-square. You got a chi-square value. Then you go and choose another random set of 25 boys, and you are collecting the data and calculating the chi-square again. In this way, you can choose n number of samples and you can have n number of chi-square values. Your sampling distribution will show the different values, the likelihood of different values your chi-square can take every time you do the study using a randomly chosen sample. I hope that was simple enough to understand. So the sampling distribution helps you to make inferences about a population based on your sample. Because the more samples you are using, more the inference would be closer to the population from which these samples were selected. Now, chi-square distribution has only one parameter, which is the degree of freedom. Again, degree of freedom is a concept that we have already studied in the IGNOU video. Maybe you can just go back and check it in case you don't remember. So if a graph is plotted with degrees of freedom in the x-axis and chi-square values in the y-axis, if we plot a graph with degree of freedom in the x-axis and y-axis we have chi-square, what will happen? The shape of the curve will be skewed to the right for very small degrees of freedom. What do you mean by skewed to the right? Skewed to the right means the tail of the graph will be more towards the right. This is called skewed graph. Since chi-square, anything that has square will always have positive values. So if you know the number line and the graph, you have positive values towards this side and you have negative values towards this side. So in this case, our graph will always be skewed to right for very small degrees of freedom. As the degree of freedom changes, the shape of the curve also changes. For larger degrees of freedom, the curve looks similar to the curve of normal distribution. Now this is what I was telling you. So this is a normal distribution curve. I hope you remember this from one way ANOVA. We said that any statistic which is parametric, if you plot the data, you will get a bell-shaped curve. This is called a normal curve. And any statistic which is parametric will have this kind of a curve. And in this case, what do we have for our chi-square? We said that smaller the degree of freedom, more skewed toward the right the graph will be. Like see here, the blue degree of freedom is 1. See the curve. This is more skewed toward the right. Degree of freedom 2. See, the skewing is still there but a bit less than what it was in case of 1. When the degree of freedom is 3, look at this, the 3. Okay, so as the degree of freedom increases, what happens? The curve moves toward a normal curve. So DF5, see, it will never become a normal curve because this is a non-parametric statistic. It will always be skewed, but the level of skewness will be less and it will be more going towards the normal curve, not exactly the normal curve. This is what it means that the chi-square distribution will have only a single parameter, which is the degree of freedom. Smaller the degree of freedom, more skewed to the right the graph will be, and higher the degree of freedom, it would be going towards a normal curve. Now let's look at the properties of chi-square test. The first property is it's a non-parametric statistical test. This means it will not meet any of the assumptions of the parametric statistical test, and hence it will not meet any assumptions about the population also. The second one is that the value of chi-square is always positive. Now this, if you square a negative value, you will get a positive value. If you square a positive value, even then you will get a positive value. So the value of chi-square will always be positive. The third property says the chi-square will be 0 only when each observed frequency is exactly same as the corresponding expected frequency. We saw the formula of chi-square. What was it? It is observed minus expected whole square by expected. When will this become 0? When this numerator becomes 0. And when will this become 0? when O is equal to E. When O becomes E and you minus it, you will get 0 by E. Anything divided by 0 is, 0 divided by any number is 0. Okay, so chi-square will be 0 only when each observed frequency is exactly same as the expected frequency. The fourth property says the chi-square distribution curve is always asymmetric and skewed to the right. This also we have seen. So what do you mean by asymmetric and symmetric curves? So symmetric curve is one which you can divide into two exactly equal halves, and this would be a normal curve which you see in parametric tests. What is an asymmetric curve? An asymmetric curve is one which will always be skewed. No matter where you cut it, you will never get a equal half. You will never get two equal halves. Okay, so this is what is the meaning of symmetric and asymmetric curves. And in our case, the chi-square distribution curve is always skewed to the right and it is asymmetric. The last property is that the chi-square distribution varies with the degree of freedom. This also we have seen that the chi-square distribution is affected by only a single parameter, which is the degree of freedom. And we have also seen that when the degree of freedom is small, it is skewed towards right, and as the degree of freedom increases, it goes on to resemble the normal curve. What are the applications of chi-square test? The first application is test of goodness of fit. This means chi-square test is used to check if a sample matches a population distribution. This means we know that chi-square distribution tells the different values different samples in a population can take. So you already know the different values of different samples from a population, and you've got a new population. So how do you know, you've got a new sample. So how do you know if the sample matches the parameters of the population? For that you do the chi-square test. And when you do the chi-square test, it will tell you if it matches the population distribution. The second application is test of independence. So chi-square test is used to assess whether one observed frequency distribution significantly differ from another observed frequency. And this checks the independence of the categorical variables in a data table. So this means we can apply chi-square test to check whether our one observed frequency is independent of the other. If you remember, this was one of the earlier assumptions that we saw, assumptions of the chi-square test, that all our observations are independent of each other. Okay, and chi-square test actually can be used to check that also, to whether one observed frequency distribution is significantly different from another observed frequency and it is not dependent on it. The third application is test of homogeneity. This means we are testing the variability of a population or whether several populations are homogeneous with respect to some characteristic of interest, like how similar the different samples you have taken are to each other in respect to a particular characteristic. This would tell you how similar different samples or different populations are. What are the precautions that you need to take while doing a chi-square test? The first one, sample size should be large enough. This we have already discussed. If the expected frequencies are too small, the value of chi-square gets overestimated. Second, when the calculated value of chi-square is greater than the critical or theoretical value at a predetermined level of significance, null hypothesis is rejected. So when we were studying one-way ANOVA, we saw that we have a table for one-way ANOVA where we find a table value using the degrees of freedom and we compare this value with the calculated value, right? Here also we do something similar. There is a table for chi-square, and after we have calculated the chi-square, we use the degrees of freedom to get a table value, and if our calculated value is greater than the critical or this table value, the null hypothesis is rejected. And if the chi-square value that you have calculated is less than the critical value or the theoretical value, the null hypothesis is accepted. So in the examination, you don't have to, there won't be any question where you will be asked to compare with the table or the theoretical value. You just need to know what happens when you compare the values. If it is greater, calculated value is greater than the critical value, null hypothesis is rejected. And if the calculated value is less than the critical value, null hypothesis is accepted. And last one, When chi-square is 0, it should be confirmed again whether the observed and expected frequencies are the same. This also we have seen. When will be the chi-square 0? When our numerator is 0. When observed and expected frequencies are the same. So it's perfectly okay to get a 0 chi-square value. Just make sure all your previous data and calculations are correct, and if it is correct, just move forward. So when your chi-square is 0, it should be confirmed again whether the observed and expected frequencies are the same. So this was the theory part of chi-square test, and you have the like, subscribe and share buttons at your disposal. Let me know if you understood everything by hitting the like button. So in the next video, I'll meet you with the computation of the chi-square. Till then, stay with me, keep learning with me. Take care. Bye-bye.